as I said in the last lesson, in geometry, one of the things we do is we kind of just make up rules and follow those rules and see what happens. So in this lesson, we're going to be setting up some of the fundamental rules that we follow in geometry. These are called postulates, also called axioms. So it's a rule that is accepted without proof. So it's something that all of us who are doing geometry just say, okay, that's true. That's something we're just going to accept as being true so that we're able to do geometry in the first place. Now, you can choose different rules. You can choose different postulates, and you can get whole different kinds of geometry. But these are the postulates that we're going to use in this class. First one is called the ruler postulate. So the points on the line can be matched with the real numbers. Which means that if you think about a number line, that's really exactly what this is. You could just take a line and throw some numbers on it, and we can match them up with any number that you want to talk about, you can find on a number line. So the number that corresponds to a point on that real number line is the coordinate of the point. Oops. So we call that location on the line the coordinate of the point. Now if we want to find the distance between 2 points, what we can do is just subtract the coordinates and then take the absolute value. So the reason why we take the absolute value is because say we're on a number line here. Say this is the point, the x value 2, and then we've got maybe 3, 4, and then this is 5. So then, 0 would be over here somewhere. So if we want to know the distance between those, well, this is simple enough that we could just count. So the distance between them is 3. The difference between 5 and 2 is 3. But if we want to kind of have a more robust way of doing this, what we can do if we want to know the difference between two numbers, we subtract them. So this works fine and dandy. If we have 5 minus 2 equals 3, that's nice. But if we were to happen to grab the coordinates in the other direction, do 2 first and then subtract 5, well, then we get negative 3. And if we're talking about distances need to be positive. And so what we do is we just take the absolute value. So absolute value makes it positive. So whichever way you grab the coordinates, just take the absolute value. This is still 3, but then this negative 3 becomes positive 3. When you have 3 points that are collinear, you can say that one point is between the other two. We looked at the word between in the last lesson. So between, again, is reserved in geometry specifically for points that are collinear, points that are all on the same line. So we can say that B is between points A and C, whereas on the right side, point E is not between points D and F. So again, it kind of looks like E is just physically between D and F, but in geometry, that word between is reserved for points that are collinear. All right, so if we have a point that is between two other points, then we have a segment that is divided up by that point. And so what we can say then is that if we take, say, this blue distance between A and B, and we add to it the green distance between B and C, what we will get is the entire line. This is called the segment addition postulate. So basically, if you take one piece of a segment, take another piece of that same segment, and put them together, you get the whole segment. It's fairly straightforward. If we look at an example of this, in example 1, you can see here we've got the red segment is 14 units long. The green segment is 20 units long. And so the blue segment, if we want to know the length of that, well, we just do 14 plus 20, and so we get 34. So that is the length of MP. Now remember, when we're looking at segments, it's important to remember that this here, where you have just the points, M and P, that means the length of the segment. If you have this with the segment above it, we're talking about the object itself. So these are two separate things. I mean, we're kind of talking about the fundamentally the same object. But when we have the segment above it, this one here, that's talking about the object itself, the segment itself. And then when we have just the points, M and P, that's talking about the length of the segment. Let's look at part B. So this time, AC is given to us, that is 47. And then we're given part of that segment, which is 25. So if we want to know the length of BC, well, we just take the entire thing and subtract off the part we know. That'll leave us with BC. So if we take 47 minus 25, that gives us 22. That is the leftover length there. When we have segments that have the same length, we can say that they are congruent to each other. So congruent is the word that we use for the same in geometry. So if you think about numbers, say take the number 4, we could say that that's equal to the number 4. But if we have two triangles that are the same, so if I want to say that this triangle is the same as this triangle, we don't say that those triangles are equal. We have a different word for that. In geometry, it's called congruent. And we use an equal sign that has a little squiggly above it. So congruence is just basically equals, but for shapes. So we say that numbers are equal. So like if we have a length of a segment, that's a number, so we would use equal for that. If we have an object, and we're talking about this object being the same as this other object, we don't say they're equal. Equals for numbers, we say that they are congruent. So looking at segment AB and segment CD here, these two segments have the same length. And that's how we figure out whether or not things are congruent, is if they have the same length. Now we have this notation here, these little lines, these vertical lines here circled in green. That notation is an indication that these are congruent. So that's how I know that they're congruent, because they're both marked with one little marking. So going back to the triangles on the bottom, so if I want to say that segment is the same as that segment, I can mark them each with 1. But if I want the segment on the right, so the one kind of slanted downwards, if I want to say that one is congruent to that one, well, I can't do it like that because now they all have 1 mark, so that would mean that they're all the same as each other. But if I just throw another mark on there, then everything with 1 mark is the same as everything else with 1 mark. Everything with 2 marks is the same as everything else with 2 marks. If I want to say that this bottom one is the same as this bottom one, I could use 3 marks to say that anything with 3 marks is the same as anything else with 3 marks. But the thing with 1 mark is different than the thing with 2 marks. The thing with 2 marks is different than the thing with 3 marks, and so on and so forth. All right, so that's what these, again, those lines right there, those little vertical lines in the middle of the segment, just means they're congruent to each other. So again, if we're talking about the lengths, so say that they're each a length of 5, well, length is a number, so in this case we're going to use equals. We would say, this length is equal to this length. Again, if we're talking about the objects, that's on the right. So if we want to talk about the segments themselves as objects, we're going to say that they're congruent to each other. Example 2, determine whether or not these two segments are congruent. So the first segment is segment JK. So we're going to use the point -3, 4, and then 2, 4. So that's one of the segments. And the other segment uses the point 1, 3. And 1, -2. So to determine whether or not these are congruent, what we're going to do is find their length. Well, nice enough. These are lying straight on the vertical and horizontal, so we can just count. 1, 2, 3, 4, 5. That has a length of 5. 1, 2, 3, 4, 5. That also has a length of 5. These have the same length, so that means that they are indeed congruent.